let me introduce to you Fabian Schmid. He was born in 1993 in Munich. That's where we are right now. He studied at the Technical University here in Munich, and since 2016 he has been working at the Max-Planck-Institut of Quantum Optics as a Ph.D. candidate in the laser spectroscopy division. That is the division of Professor Theodor Hänsch. He actually got a Nobel Prize in 2005 for the invention of the frequency comb. The frequency comb allows to measure frequencies ultra precisely. For example, the frequencies of electromagnetic radiation, which is light, for example. Fabian's group focuses on precision spectroscopy of hydrogen or hydrogen-like ions. These are the simplest of atoms because they have only one proton in the nucleus. And in contrast to normal hydrogen, hydrogen ions don't even have an electron. That is why they have a positive charge written as H+. These simplest of atoms, hydrogen and hydrogen-like ions, allow theoreticians to make very precise calculations of their properties. These calculations are based on the theory of quantum electrodynamics, which describes the interaction between light and matter. By comparing experimental results from precision spectroscopy with theoretical predictions, the validity of those theories are for sure tested. So the availability that we have here with precise calculations in theory and very accurate measurements in our labs, combined, these two, the calculations and the measurements in the lab, they make quantum electrodynamics actually one of the most stringently tested theories in physics. The aim of Fabian's experiments is to measure the frequency of one particularly narrow spectral line in hydrogen-like helium ions. Spectral lines are the result of the absorption or emission of light by the atoms, as well as by molecules. They are kind of like their fingerprint, like the spectral lines that show up. Fabian's experiment makes use of the fact that the contrast to neutral hydrogen atoms, charged helium ions can be held nearly motionless in an ion trap. So let's meet Fabian and learn more about laser spectroscopy, his ion trap, and hydrogen-like ions.
Okay, hi. Welcome to the Helium Plus lab, where we are currently still setting up an experiment that's not running yet. But before I begin to start you the actual setup, I'd like to give a short introduction into what it is that we're actually doing here. So we're doing a laser spectroscopy of helium, hydrogen-like helium. So let's start with the first thing. What is spectroscopy? So this is kind of the 19th century spectroscopy. So you put some atoms into a glass tube, then you pass some electrons through them with a high voltage supply, and then they somehow emit light. And people have noticed this, and they were interested in what colors of light they emit. So you take a prism to disperse the colors, and then you get here some pattern, which is called a spectrum. And they very soon realized that atoms actually don't emit just a blur of colors, but they have so-called spectral lines. So they emit very well-defined sharp colors. In this case, it's sodium atoms. So there's a sharp yellow line, very strong. This is what makes sodium lamps yellow. They were used, for example, in old street lights. And one particular atom has been always fascinating, which is hydrogen. It's the simplest atom because it only has one electron and a proton. And it also has a very simple spectrum. So these are the visible spectral lines of hydrogen. So there's a red one, blue, some violet ones, and then a lot of UV and infrared lines that you cannot see with your eyes. And already in the 19th century, people noticed that there's a very regular pattern in these lines. So if you take the inverse of the wavelength, there's only a single constant in this formula, and then the square of two integer numbers. And all the lines lie on values predicted by this formula. So that's, of course, very strange, and for a long time, people didn't know why this is the case. And in a way, the hydrogen atom has then become the Rosetta Stone of modern physics, because you always need some object where you can test your theories on. So you need a simple atom. So the first thing that you might have heard of is the Bohr model of the atom from 1913. So he described the atom as a nucleus with the electron orbiting around, like a planet around the sun, but only certain orbits are allowed. And when the electron jumps between these orbits, then the energy difference of the orbits is emitted as light, and this is why we have sharp spectral lines. And this, with some other arguments, he could already explain where this formula comes from for hydrogen. Problem is, this theory basically contradicts all of physics that was known at this time, so new physics had to be developed. And this was quantum mechanics. So Schrödinger basically treated the electron here no longer as a particle, but as a wave, and he formulated a wave equation called Schrödinger's equation, and with this equation he could show that indeed he also recovers these spectral lines in hydrogen. And now we don't have these orbits anymore, the circular orbits, but we have these, this is called the wave function of the electron. These are these orbitals that you might have seen in chemistry. So these are probabilities where the electron is. Now there are still some features in the spectrum that this cannot explain. So one of them is that if you look more closely at this red line, for example, there's actually two lines. There should be one, but there are two lines. And this is called the fine structure. And already 2 years later, Dirac was able to explain this. So the Schrödinger equation is still extremely important. It's the fundamental equation of quantum mechanics, but it's non-relativistic. It doesn't take into account Einstein's theory of special relativity. And if you do that, which is what Dirac did, then it turns out that the electron, which is just a point particle, behaves as if it was spinning and has is a small magnet essentially. And by calculating or solving the Dirac equation for the hydrogen atom, Dirac was able to show that this produces this fine structure splitting. So again, this was a very convincing argument that this theory is actually correct. And then by the late 1940s, became clear that even Dirac's equation is not completely correct. So they found that there were transitions in the hydrogen atom that shouldn't exist according to Dirac. Some radio frequency transitions. And to explain these, so in this model, the hydrogen atom is a quantum particle, but the light is still classical. It's a classical field. And to explain these effects, you also had to introduce a quantum theory of light, and or quantum theory of the electromagnetic field. And this theory is then called quantum electrodynamics. And to this day, this is the theory that describes best the interaction of light and matter. So this is basically the modern version of this simple equation. And so quantum electrodynamics is not an easy theory. It's not something where you can write down a few lines and you have it solved. So this is the simplest of all atoms. And there's actually experts that derive these equations. So it's not something that you can just do in an afternoon. And this is many, many years of work. And it's still not finished. So some of these terms are just stopped when the accuracy was good enough. And when the measurements get better, for example, then the theorists will sit down and calculate more terms to make the theory better. And what we are doing in this group is we are measuring the frequencies or different transition frequencies in hydrogen and hydrogen-like systems. And they are all described by this theory. And if we have enough of these measurements, then we can essentially check if this theory is correct. So that's the purpose. We want to test the best theory in physics. Now, so far I've not talked about any lasers, and this is of course not how we do spectroscopy today. So let's talk about laser spectroscopy. So one thing that people also realized very soon already in the early 20th century is that atoms, if they're excited, they emit light. But it can also go the other way around. If you have a light source that emits light exactly at the frequency of a spectral line of an atom, so if your light, for example, has exactly that color, then the atom will absorb these photons and re-emit them in a different direction. And at some point in the late 60s, lasers became available where you can tune the wavelength such that the wavelength of the laser coincides with the spectral lines of the atom you want to look at. And then the setup looks a bit like this. So you have a laser, you send your line through your atoms, you look for how much these atoms emit light, and then you can change the wavelength of the laser. You somehow have to measure that change, and then by scanning the frequency of the laser in and out of resonance, you can produce a plot like this. So this is the wavelength of the laser, this is the intensity of the light emitted, and these are the spectral lines of the atom. But now you can have much higher resolution. So one advantage is you can choose in what kind of situation your atoms are. So if you're hitting them with electrons, you're heating them up a lot. They have to be very dense to make enough light and so on. And this is all leads to blurring and shifting of these lines. So now if you have a laser, you can get by with very small amounts of atoms, and you can cool them down. And this has enabled a much higher resolution spectroscopy. So this here, these lines are actually the 2 lines I've shown before. So actually it's not 2 lines, it's many more. You just couldn't see them because the instruments were not good enough. So this again shows that you need, it always helps to have better instruments if you want to learn more about physics. And there's still one ingredient missing that would be very cool here. One problem here is we are still measuring the wavelength of light. And measuring the wavelengths, it's a size, you have to measure a length, and we cannot measure lengths very accurately. So lengths are just not a quantity that are easy to measure. So what would be a lot better is measuring the frequency of light, because frequencies are by far the quantity we can measure the best. So with atomic clocks, we can measure frequencies with 16 digits of accuracy. No other quantity in the world comes close. And for a long time, this was extremely hard because, of course, the wave that comes out of a laser, so it's just an electric field that is oscillating, has a frequency of around 500 terahertz, which is an extremely high frequency. So this is hundreds of thousand times faster than what detectors or electronics can see. So you cannot just plug in your oscilloscope and see this wave. And for many decades, there were possibilities of measuring the frequency of lasers, but it was extremely difficult. Only a handful of groups in the world did it, and it always was one setup for one particular wavelength, so not at all flexible. And then in the late 90s, here at MPQ actually, in the Hänsch group, there was this development of the frequency comb. So this was developed in the Hänsch group by Thomas Udem, who is still my group leader here, and his colleagues. And this frequency comb is also a laser, but it produces pulses of light instead of a continuous wave of light. And I don't want to go into too much detail here, but with a very clever optics and electronics, you can make it such that these pulses have a very regular spacing. So they always come after the same time interval. And also the exact shape of this electric field is always, you always can control it exactly. And both of this, you need electronics and reference it to an atomic clock. And now if you overlap a frequency comb pulses with a continuous laser, then you get an interference out, because these are both waves, they interfere. And this interference signal is in a range that you can measure with electronics and detectors. And from this signal and the settings here that you use to control your comb, you can directly measure the frequency of light. And this works for essentially any laser wavelength, so it's very universal. Frequency combs are compact, so this has really revolutionized spectroscopy. And for this also Professor Hänsch was then awarded the Nobel Prize in 2005. Okay, so a few more words about what we're doing in here. So as I said in the beginning, we're doing spectroscopy on hydrogen like helium, not hydrogen. So this is a hydrogen atom. And if you now take helium, which has 2 electrons, and you remove 1 electron, then you have hydrogen like helium. So it's essentially the same same object, except with a different nucleus that is a bit larger and doubly charged instead of singly charged. And doing spectroscopy on helium ions instead of hydrogen has a number of advantages. One of them is that this charge allows you to hold these atoms in space, and which I will show you more about later. And this can be very good for achieving more accurate spectroscopy. And then there are also other reasons, like you want to check if your theory actually also works for such particles. Maybe the theory only works for hydrogen. Nobody ever checked it in helium plus. And one thing that makes helium plus very difficult are the wavelengths that you need to drive the transitions. So the one very interesting transition in hydrogen, the 1s-2s transition, requires a laser at 243 nanometers. So the visible spectrum goes from 800 to 400 nanometers. So this would be somewhere here in the deep ultraviolet. This is hard to make, but you can buy such a laser. It fits on your table. It's not so hard anymore. Here we need a 4 times shorter wavelength. And so this wavelength is 61 nanometer. And this is extreme ultraviolet wavelength, which is very hard to generate. And actually this whole table here, which is in this box, this is only the laser system to generate a 61 nanometer light. And one thing I should mention is what we're doing here is, come back here, So as I said, typically you would use a continuous wave laser to do the spectroscopy, measure the frequency with a comb. Here we don't use the continuous laser. We directly shoot with a frequency comb at our ions. And for some types of transitions, this behaves very similar to a continuous wave laser. So we kind of skip this part. We directly have a frequency comb. And we want to generate a frequency comb at 61 nanometers with which we can drive our excitation. Okay, so then I think we can start with the setup, and I will explain more as we go. So this whole thing is in a so-called flow box. So there's filtered air coming from the top to avoid any dust, because we have a high power laser in here, and dust would destroy the mirrors by burning into them. So the first component where the entire setup starts here is this orange box. This is a frequency comb. This is from a company in Munich, a commercial frequency comb that you can buy. And this is not a 61 nanometer laser, but it's actually an infrared laser at around 1 micrometer wavelength. And then the light comes out here, travels into this big silver box. And the silver box is a laser amplifier. So it takes the already powerful frequency comb, which has about 3 watt average power, and amplifies it up to 400 watt average power, which is really a lot for a laser. And then the light goes into these 2 long silver boxes, and these have the purpose of making the pulses shorter. So as I said, a frequency comb makes pulses instead of a continuous wave. And if you want to have the highest intensity possible, so as much light as possible in a short time, you have to make your pulses shorter. This is what these boxes are doing. As I said, we don't directly have a laser for 61 nanometers, so we have to do what's called frequency conversion. This is actually quite common in an optics lab. For many wavelengths, you just can't make lasers. So you have to somehow else make the wavelength. So here we start at a 1033 nanometer, an infrared laser. And if this is a very intense pulsed laser, like a frequency comb, and you focus it into a jet of gas, xenon atoms, then there's a process taking place called high harmonic generation. So this has to do with very intense fields very strongly interacting with the atoms. And then this generates all kinds of wavelengths. And these are all higher frequencies. So this is 1/30 wavelength, 3 times the frequency, 5 times, 7 times. And the light we want to have is the 17th harmonic, which is then at 61 nanometers. And this is why we need, in order to get enough intensity to do this process, we need this big amplifier and this pulse compression scheme here. And then finally, the light goes onto this optical setup here, and then goes into this vacuum chamber. So this is pumped out, no air inside. And the reason, from here on, everything is in vacuum in the setup. And the reason for this is that 61 nanometer extreme ultraviolet light gets absorbed in air. So you cannot propagate it through anything really. No gas, no windows. It's very hard to work with it. And in here is actually an optical resonator. So there's a set of mirrors where the pulses bounce back and forth. And in this way you can enhance the intensity of light you have available. And we need all this just to have enough intensity to be able to drive this high harmonic generation process. And this is actually the gas bottle which contains the xenon gas, in which later, so there's a tube going into this chamber, and then there's a jet of gas where the high harmonic generation can take place.
So the question here is, how powerful should the pump be to get a high harmonic generation?
So there's a certain intensity threshold. What you need is intense pulses. So what you can do is, what we are not doing, we have a lot of pulses per time. We have 40 million pulses per time, 40 megahertz. And we also need that for our experiment for some reasons. And what other experiments often do is they combine many of these pulses together in stronger pulses. So if you take, for example, 1,000 pulses and put them all into one pulse, then it's 1,000 times more intense. And then you can do high harmonic generation with watts of power, average power. But here, since we need these many pulses per second, we need very high average power, which is around 300 watt at the output of all of this. And inside this resonator, we actually have many kilowatts of circulating power. So it's really a very powerful laser. I hope that answered the question. So now we can go to the second part of the experiment. This is kind of the spectrometer where the actual spectroscopy takes place. So first of all, here you can see the connection tube. As I said, everything has to be in vacuum, so the extreme ultraviolet light has to pass through a vacuum tube. And in here there's a big mirror. This is the mirror for steering the extreme ultraviolet light through the rest of the setup. So somehow we have to adjust where we are shooting the light. And then we have here 3 more vacuum chambers. 2 of these basically only contain mirrors for sending the XUV light in the end onto our ions. And the ions are stored in an ion trap. So this looks something like this. So this is an older version of our ion trap, or a test model. So this is a so-called Paul trap, which was invented in the late 50s by Wolfgang Paul, who was awarded the Nobel Prize in Physics for this invention in the 90s. And the way it works is you apply high voltages to these electrodes, and then these triangular electrodes here, you apply a radio frequency to them with some tens of megahertz frequency. And if you do that in the right way, which kind of depends on what you want to trap in them, then an ion that is in between all these electrodes here in the exact center cannot escape. So it's trapped, as the name says. And this is a big advantage of helium plus over hydrogen. So for helium plus, you can easily trap it. Hydrogen would be very hard to trap because it's a neutral atom. And many other techniques like optical lattices don't work very well for hydrogen atoms. So this is one of the reasons why we are interested in helium plus instead of hydrogen. So this trap is in this vacuum chamber here, but there's a lot of stuff around it, so you cannot really see it.
Would you point it with the laser?
So the ion trap is in the middle of this vacuum chamber. So I don't know if you can see anything through the window.
Tiny little bit.
Yeah, it's right behind this window. So because you can't really see it, I have a picture. So this big flange here is the bottom plate of this vacuum chamber, so that you can have an idea. And this is this ion trap where I've just shown you the model. So it's right in the center of the vacuum chamber. And then surrounding the ion trap, we have an electron gun here. And this is needed to make helium ions. So we put helium gas into the chamber, we hit it with electrons, then we have helium ions. One other complication is we also need different ions in our trap. So helium ions are nice, we can trap them, but as I've just shown you, it's very hard to make a laser that interacts with helium ions. So we cannot see them and we cannot cool them in the trap. So to do that, we mix the helium ions with beryllium ions. And this here is an oven where a small piece of beryllium is heated up. Then we have beryllium atoms flying into this trap. And then we have a laser that can ionize beryllium to give us beryllium ions. And if you do that, you get something like this. So this is a so-called ion crystal. So each spot here is one beryllium ion. And they are illuminated by a laser that is resonant with a transition in these ions, as I've shown you before in the spectroscopy. And this makes them emit a lot of light. So they are fluorescing very bright. And this is why we can actually see single atoms on a camera. And another effect that this has is that there's laser cooling. So if you do it right, shine a laser on these ions, they lose all of their kinetic energy and they become extremely cold. So these ions have only a few thousandths Kelvin above zero. And if we now add some helium ions here, then there's a kind of a gap in between the beryllium ions where you don't see anything. And this is where the helium ions are sitting. And because we don't have a laser to make them fluoresce, we don't see them. But because we have the beryllium around them, this is one way we can identify that we actually have helium in our trap. So this is one purpose, just being able to see something. The other purpose is just for cooling. So if you surround your helium ions with cold beryllium ions, they also get cold. Otherwise, it would be extremely challenging to laser cool helium ions. So this is and this in the end will be the target in our spectroscopy. So the extreme ultraviolet light will fly along the center of this ion crystal from both directions and hit the helium ions in the center, and then hopefully drive this 1s to 2s transition that I've talked about before. So let's see, what else do we have to show? Maybe if we come around the corner here, we can have a look at the cameras. So these are the two cameras that we have for looking into our ion trap. So one of them is looking from the top over a mirror here, and the other one is looking straight into the chamber through this through a window here. And so in the beginning of these tubes, there's an objective for imaging. I think you can't really see it. And then it forms an image on these cameras. These are special cameras. So they use the same kind of technology as your normal digital camera, but they are cooled and amplified, which allows them to have a very low noise and to basically see individual photons. So this is what you need to make nice images of your ions. Yeah.
What are these optics for up there?
Yeah, very good question. So this here is this fiber. So as I said, we are shining near resonant light onto the beryllium ions, and this fiber delivers that light. So it's this thin, unprotected, very delicate glass fiber. This is a special fiber that can transmit ultraviolet light. Most glass fibers can't do that; they would be destroyed. We actually had to manufacture it here. It was not so easy. Unfortunately, you cannot buy them yet because the market is too small. So we had to make them ourselves. And then the light here. These are all kinds of optics for distributing this light in various directions, because we might want to have cooling lasers going in from different directions onto our ions. So we have a beam, for example, that goes diagonally here. So it goes in through this window. And we have another beam that actually goes all the way through the setup and goes basically like this. So it goes through all these chambers along the axis of the trap. And just for distributing all this light everywhere, we need a lot of optics. So here, these are the mirrors for sending the ionization light in, for ionizing our beryllium ions. And the things on the other side are mainly imaging. So these are the main things that we need it for.
So there was the question, have you yourself put all this together? And if so, how long did it take?
Okay, so the question was if I built all of this and how long it took. So this part of the setup already existed. Part of this part already existed when I started here, and this was mostly built by a postdoc of us. This table was empty when I started, so everything on this table was put together by a postdoc and me. And we started with this vacuum setup, I think, in early 2017. Here, this table I haven't talked about yet. This is where the lasers are. So we also need not just this big laser for helium plus, but also lasers from manipulating beryllium and beryllium plus. So this box contains a laser for ionizing neutral beryllium, and this box contains the laser for laser cooling beryllium plus. And this laser I built, and this one was already built for a previous experiment, and we modified it a lot to make it more stable, more powerful, all of these things.
Can you show it to us?
Sure, I actually even have a drawing. Okay. So, yeah, fortunately we turned everything off so we can open the boxes. Here we have to generate a wavelength of 313 nanometers in the end. This is also ultraviolet, not very deep ultraviolet, but still there's no laser that directly makes this. So again, we have to do frequency conversion. And in this case, we start with a 1050 nanometer and a 1550 nanometer laser. And these are these two. These are so-called fiber lasers, commercial products that you can buy from a company. This one is maybe 1 year old, this one 10 years old. And so they have optical fibers, and they send infrared light into the setup here. And so there's one laser's coming out here, the other one here. And then the light is overlapped here in this oven. So this is an oven, and in here is a crystal, a special nonlinear crystal. And if you have the right crystal at the right temperature with the right wavelengths and so on, polarizations, then you can do some frequency generation. So what basically happens is you take one photon from this laser, one photon from that, and you add them together. So the energy adds up, and then you have a photon at 626 nanometers. So half the wavelength, twice the energy. And so we are halfway there. And then we still need to frequency double this to get to 313 nanometers. And this happens in this part of the setup. So the red light that we produce here travels all the way over here, here, and goes into this box. And in this box there's also an optical resonator, so a number of mirrors. And if you have to actively stabilize the position of these mirrors, so there's some electronics up here and some detectors. And if you do that properly, you get a resonance. So you have a standing wave of light with very high intensity. And if you then place a small, again another kind of crystal in this light, then there's some nonlinear interaction happening that frequency doubles the light. So from the 626 nanometer you get 313. So that would then come out here. And then we have all kinds of modulators that we need for various reasons, switches. We distribute the light, and then at the back here, here's a glass fiber, one of these unprotected thin fibers. Here's another one, so we can send this light to two different setups actually. One of them is in a neighboring lab, and this is how the light then across this cable bridge, the fiber then goes over here and ends up here and delivers our cooling laser in the end. Yeah, are there any more questions?
Yeah, are there more questions? Anyone, anything else? There was the question from the beginning that has been actually tried to be put more precisely. I have to find it. In Dirac's equation, there was like this question with, please explain a little bit about the negative in Dirac's equation. Does that make sense?
Yeah, so Dirac's equation doesn't only contain electrons but also positrons. So there are solutions of Dirac's equation that have negative energy, and Dirac initially thought that's unphysical, that must be some kind of something that nature doesn't do. But later on in cloud chambers, people discovered that there were particles that behaved like electrons but bent the other way in a magnetic field. So these are positively charged electrons, positrons, and this is exactly this negative solution of Dirac's equation. So it turns out he kind of accidentally predicted a new particle, and that was later detected.
And then there's a question, what is the thing that you are most proud of?
Yeah, I think building this whole setup is some achievement. Unfortunately, we are not there yet. We are not ready to do measurements yet, but I think it's already quite an impressive setup, and some parts actually work, so I'm proud of that.
And then there's the question, and what is the most annoying thing you would say?
Here in the setup. So what I don't like is that one problem I was fighting with a lot is that these crystals, especially if you hit them with ultraviolet light, they break all the time, and it's very hard to get nice ones, and they're expensive, and it's very fiddly to align this, so I spent a lot of time rebuilding and realigning this thing until I found crystals that work. That's my current annoyance in the lab. In general, UV light is not very nice because it breaks everything. It's very aggressive. I would prefer to have like rubidium atoms with a nice infrared laser that makes things easier.
Which one was it in Maimann's laser?
Maimann's laser was red.
Was it rubidium?
No, ruby.
Ruby.
It's a ruby crystal.
Yeah, right.
So rubidium is one of atom that is very popular for cold atom experiments because it's so nice. So it has a very convenient wavelengths, very convenient properties, but it's not hydrogen. So it's very complicated, dozens of electrons. There's no way of calculating it with the kind of precision that you can calculate hydrogen. So that's why we are not using rubidium.
Then there is the question, what is the aperture size of the lens?
The question was, what is the aperture size of the lens? Probably he's referring to this objective, and these are 2-inch lenses, so about 5 centimeter aperture size. But there's a little bit of an aperture stop to reduce aberrations. If anyone knows about photography, if you have a too large lens that is not quite good enough, then you get errors in your image. So you can make the lens a bit smaller. So here it's maybe 3 centimeters or so. Then you get less light, but a nicer image.
Here's the question, I don't know if it relates to the question before. Is it needed to focus very tightly on the ions, few microns?
Okay, the question was if you have to focus tightly on the ions with the size of a few microns, and yes, that's actually the case. And the nice, that's one thing where having ultraviolet light is very nice, because the shorter the wavelength of light is, the easier it is to focus and the less it wants to spread out. So 61 nanometer light, we can actually focus down to a few micrometers, even though it's very far from where it's generated over here. Then it has to propagate very far, and then in these two chambers are, so here's a mirror, so the light goes all the way through, past everything. Here's a curved mirror that focuses the light onto the ion trap here. Then it goes back into this chamber, and here's another curved mirror that focuses the light back, because we need to have light from both directions. And with these curved mirrors, we can achieve focus sizes of a few micrometers, mainly because the wavelength is so short. This makes focusing a lot easier than for visible light, for example.
In a few and simple words, what is the ultimate goal of your research?
Yeah, so the ultimate goal is as I've shown in the beginning, is checking quantum electrodynamics. So as physicists, we always want to find something new, really fundamentally new in nature. And one way is to go into very high energy, like in a particle accelerator, and try to see some new effects. But one other way is just to look more closely. So if you have a system where you can do accurate calculations and accurate measurements, then you can easily see if there's a mismatch. And the hope would really be, or the dream would be, that you find, okay, there's something wrong with quantum electrodynamics. We have to find a new theory. That would be great. But so far, QED is annoyingly robust. So it's a theory that has progressed over decades, has been tested more and more thoroughly, and it always stood up to the test. So it's really an interesting phenomenon. Let's see if we find that something wrong with it.
It seems to be quite something that research is a lot about not proving things, but actually doing the opposite of that, isn't it?
You can just not disprove it, but that's kind of how science works. So yeah, you can only disprove things. So that would of course be great to see that there's something wrong. And of course, on the way, you learn a lot about technology. For example, the frequency comb was developed to do hydrogen spectroscopy. And nowadays it has all kinds of applications in for example, the next generation atomic clocks will heavily rely on frequency combs. They wouldn't be possible without. And also on the theoretical side, if we are pushing harder on the measurements, at some point this, so on the other side, this equation is not good enough anymore. So here there's many terms, but this is actually an infinite equation, so you have to stop at some point. And you cannot just let a computer write this down, but people have to calculate all these terms. And when you have now reached the limit of what this equation can do, then the theoreticians have to sit down again and calculate more terms. So this is also an incentive to develop new theoretical techniques. So it's really a very rich system, even though it's so simple.
And then there's the question, how do temperatures affect the apparatus?
Okay, the question is how temperatures affect the apparatus.
The apparatus, the whole thing.
Yeah.
And probably dust as well. I'm wearing shoes.
Yeah, so I think I've already talked about that. So this box here contains, is filtered to avoid dust ingress. And that's also why we have overshoes. Or I have clean shoes that I don't wear outside. And the reason is that dust would destroy these mirrors. If a high intensity pulse hits the mirrors, burns the dust, and it burns into the surface of the mirror. And temperatures, yeah. So if temperatures fluctuate in this lab, it's a problem because the optics gets misaligned. So we have very nice mirror mounts, but still there's always a bit of thermal expansion. So that's why all labs at MPQ are air conditioned to keep the temperature as stable as possible. And completely different thing, temperature, our ions also have to be very cold. So they don't have to be just stable, but extremely cold. This is because hot atoms are moving back and forth, and this creates so-called Doppler shifts. So if the atom is moving against a wave, then it sees a different frequency than if it wasn't moving. And this equation is true for an atom that doesn't move. So if we have Doppler shifts, then we get a broader line, so it's harder to find the center of the spectral line. And there's also a so-called second order Doppler shift, which is called by relativistic effects. This really shifts your line away from where it should be. So of course we have to make our atoms or ions as cold as possible to get accurate spectroscopy results. And for helium plus, we hope that we can reach millikelvins, thousands of a Kelvin. For hydrogen, so far that hasn't been reached. So they are using really a jet of atoms, and they are cooled by liquid helium, and they only reach a few Kelvin, so 1,000 times hotter. So this is a big limitation for hydrogen spectroscopy that we wouldn't have for helium plus, because we have it in an ion trap and not just in a beam flying around.
And I would say this is the last question. How does it feel to work with a Nobel Prize winner?
Oh, okay.
Would you stand in front of your apparatus?
Yes,
just to
of course.
have you in front of it, it's just nice.
Yeah, I think it's very great, right? It's always awe-inspiring to have someone that famous as a group leader, and yeah, it's very nice. It's also a great institute, of course. It's not just this group, but all the other groups, of course. We have excellent workshops. We have a lot of money and things like that, nice infrastructure. So it's very good to be at such an institute.
Thank you. Thank you. I'm going to show you around the machine one more time. So you get a last view of how all this looks, all these optics that all have a meaning, that all have a reason to be there to get the right properties of light and laser and wavelengths for the research. I really hope you will join us again tomorrow. Tomorrow it will not be a lab tour, but it will be a talk between Ignatius Dirac, the director of the theory division, very famous for the first working concept of a quantum computer, and of Flora Kunst, who is a postdoc at our institute. So thank you very much for joining us. I hope you enjoyed it. I'm pretty sure you learned a lot. I learned a lot again today, and I'm hoping to see you again tomorrow. And again, thank you for joining us, and see you tomorrow. Bye-bye.